All right, let's get started. So the programming test 3 is out. I released it, I think, Saturday afternoonish, somewhere around there. So programming test 3 is out. It's all about linked lists, so feel free to check that out whenever you'd like. And let's start talking about linked lists. So to talk about linked lists, before I talk about that, I want to do I forgot my one announcement. I won't dwell on it like I did last time, but remember, quiz in lab this week. I'm telling the TAs, if anyone shows up more than 10 minutes late to turn you around, not late to take the quiz, please show up on time. And that's not going to dwell on it this time. But I just want to make sure I say that in front of lecture 2 times, in front of both lectures, just so if anybody's late and complains about it, I can at least say that I did say it. All right, array list and array. I'll talk about it a little bit. Sometimes I do forget to talk about policies like that in lecture, and then somebody gets turned around, and then they get reasonably upset. Like it's reasonable that they get upset if they're like 15 minutes late and they can't take the quiz. So I like to make sure we're all on the same page with that going in. It's not the TAs being rude or anything. That's my policy. You got to be on time to lab. All right, so array list and array, and most of this does apply strictly to arrays. We don't really use arrays much in this class. You will in 220, for what it's worth. And that's where we'll have to think about what the array list class does for us, because the array list class does a lot for us. So arrays are sequential data structure, meaning that the order matters. If you insert an element into an array list, you expect it to be the last element, and you expect that order to be preserved. What makes arrays kind of special or unique, what makes them arrays, is that they're one continuous block of memory. So when you have an array and you have 5 elements in your array, those 5 elements are sequentially located in memory. When you have a chunk of heap space for your array that stores 5 elements, it's one block of memory, and what you actually get is the memory address of the first address in memory, the address of the first location in memory of that array. You don't get a memory address that stores the whole thing, and that's true for all our objects. We have the location of the first byte of that block of memory, and then we use that to find all the values stored in that object. With arrays, this really helps us out in finding a specific element at a specific index. When you ask for a value at a specific index, you can calculate exactly what memory address that value is located at least the first memory address of that location. So we have the first memory address of the array itself. That's what we store in our variables, is just the first memory address of that array. And then if we want to find the value at any index, we take that index, multiply it by the size of a single element of that data structure, depending on what type it's storing, and then add that to the first memory address. That gets us immediately the memory address of that index. So if our index is 0, this zeroes out, and we get the address of the first memory address, and that's where we find the element at index 0, the first element. And if you're ever wondering, that's why our indices start at 0. So this index math works out really good, works out really slick. So we can randomly access any value in our array. And the trade-off, data structures are all about trade-offs. Any data structure you learn, there's no one be-all, end-all data structure that's perfect for everything. Data structures are always trade-offs. What do you want to do is going to determine what data structure is going to be the most efficient for that solution. So the downside of an array is that it's fixed size. You cannot change the size of an array. No matter how hard you try, you can't change the size of an array. An array, you go to your operating system. It's an object on the heap, so you have to go to the operating system to get memory allocated for it. And when you go to the operating system for memory, you have to specify how much memory you need. So you go to your operating system, you say, hey, I need enough memory to store 5 ints in an array. It'll give you enough space to store 5 ints. You can store those 5 ints, and if you need a 6th int, you're out of luck. You can't go to the operating system and say, since it gave you this chunk of memory, you can't say, hey, can I also have the next little chunk of memory so I can store a sixth int? It's not going to work like that. It's not going to do that. The operating system's going to go, tell you to, just go away. When we ask for heap space, we ask for a specific amount of space. The operating system's going to give us, or the JVM, I always say operating system since it applies to any language. But the operating system is going to give you a chunk of space. It will allocate however much space you asked for somewhere in memory. We have no control over where in memory it gives us that space. We can only ask for an amount of space. So we get a memory at some location, allocates that much memory for us, gives us the memory address of the first byte of that chunk, and then that's ours. The next chunk of memory for that array that we would like to use might be used by another program. The operating system might have gave it away to somebody else, might have gave it to our own program for one of our other objects. We don't have access to it. We cannot say, give us this specific memory. We can only say, give us this much memory. But an array list can change size. We know that. We've used array lists. You've used array lists and you've changed their size. You've added elements to the end of them, and it created the next index. Array list has a whole bunch of stuff going on internally that gives you the illusion that an array can change size. But an array list is not an array. It's an array list. It's also not a list. It's very confusingly named. But it's a data structure that works with an underlying array. And we actually did see this when we looked at the array list class. We saw that it had two instance variables. One was a plain old array, which has the property you can't change size or anything. And the way an array list works, I'll give my short explanation of the way it works, but you'll spend several lectures on this in CSE 250. The way an array list works is it creates an array that's bigger than it needs to be. So it creates more space than it needs to store your elements, and then we'll store your elements in the next available index. And then once that array fills up, if you try to add another element to it, what it does is goes back to the operating system and say your array is 5 ints. It'll go to the operating system and say, hey, I need a new array. Give me a new array that can store 10 ints. Take those 5 original ints, copy them into the new array, and then add your 6th element to the end of that, or not to the end of that array, but at index 5 in the new array, and now it has 4 empty slots for your next 4 elements. If you fill that one up, it says, give me an array of size 20, copies the old array values over to it, but it's always going to double the size of the array after it runs out of space, and keep doubling until you're done adding elements. But it won't change the size of an array. It'll create a brand new array, copy all the elements over, and then use that new array from then on and let the old array get garbage collected. So it's fairly inefficient whenever it has to resize. It has to create a new array, but it's the way it has to be done. And that's how the array list gives us an illusion that an array can change size. It's by throwing away the old array and creating a brand new one of the new desired size. And if you were really keen, you're really watching close when we looked at the array list class, you noticed that second instance variable, size. It was an int called size. Why would you do that? Why wouldn't you just ask the array for its size and use that as a size? Well, that's why. The array is almost always going to be, the size of the array is almost always going to be out of sync with the size of the array list because it's bigger than it needs to be. So getting the size of the array isn't very helpful because it has a lot of empty spaces that are waiting to be used that aren't used yet. But the size variable is going to store the actual size of the array list, the number of entries in that array that are actually being used. So that's where my conversation will end on that, but a lot more in CSE 250. When you analyze the runtime of that and realize that doubling and reallocating actually isn't that bad. It's called amortized runtime. You'll hear all about it. But fixed size is the key takeaway here. And in our memory diagrams, we represented an array list like this. We had this T-chart with our values all sequentially written. And that's because that's actually how this thing's stored. It has the values all co-located in memory, or at least by indices. They are a sequential chunk of indices in memory. And to break this down a little further, our index, our memory address, which is just an index in memory. Remember, RAM, our memory, is one giant array. our memory addresses are indices for bytes on that array. It's one big array of bytes, and we have indices where we can access one of those values. So if we have an array list of ints are 32-bit values in Java, which are 4 bytes. So if we have the index for the first memory address of the array list, that's the index of the first memory address. If index is 0, this wipes out to OX200 of the first element. And then the memory addresses OX200, OX201, OX202, OX203, those are going to be the 4 bytes for our first int in that array. If we want, say, the value at index 3, we're going to do a little bit of math. 3 times 4 is 12, plus OX200, the index of the first element of this array. That's going to give us 212. We go to memory address 212, 213, 214, 215. Those are the bytes for that fourth int in the list, or in the array, which is the value at index 3. So with a little bit of math, 1 multiplication, 1 addition, 2 operations, we can get to any value in this array. This is called random access. It's very fast. With 4 elements, okay, big deal. But if we have, say, 1,000,000 elements in this array, and we want to get the 800,000th element, or the value at index 800,000, it's still just a multiplication, an addition, and then we go right to that memory address. This is random access, meaning we can access any value at any index with the same efficiency as any other value at any other index. And since we can very quickly compute where we can find a value given its index, this is a very fast lookup time. It's a O of 1 runtime. You might not have seen big O notation yet, but it's very fast. It's a very fast lookup. If you have, this is O of 1 lookup. And since memory is a giant array, it also has random access, which is why we call it random access memory. RAM, random access memory, it's one giant array of bytes, and that's where all of our memory goes, stack and heap. Yeah.
So you can make array with some strings, right?
Yep.
How does it work with that? Because strings can be of any size.
Yes. So how does this work with strings? Good question. So this is kind of the details we sweep under the rug with strings. So to have a variable of type string, it is actually a reference to a string object, and references are fixed size. So we can have an array list of strings because it's references to strings. We are pretending that they're primitives just for our memory diagrams, but that's another case where, it kind of falls apart a little.
If it wants to access the fourth string, it just goes to what's the size of the reference in bytes?
I don't know off the top of my head. I feel like it's 8 because we have 64-bit machines now. I think that correlates right to the memory addresses. But I'm not 100% on that. I'm not a hardware guy, so I believe so. Yeah, yeah. Whatever the size of a reference, references are a fixed size. I think they're 64-bit because we have 64-bit machines, but I could be wrong on that. I think that's how it works, right? I don't know. It's been a while since I thought about hardware. But I'm pretty sure that's what the 64 means a lot. It means the CPU takes 64-bit operands, but I think the memory addresses just work as operands. Is it confirmed? Cool. 8 bytes, 64-bit. Cool. Confirmed. I like confirmation. All right. And I said everything I wanted to say on this slide. So all that just to motivate the differences between array lists and linked lists. Why are we learning a second data structure? Well, I'll give my disclaimers right now. We're learning it partly just because it's a computer science thing that you're expected to know if you're going to be a computer science student and get a computer science degree. But it is also nice to know the fundamentals. The concept of a linked list is very good to know, but we are going to create our own linked list from scratch. We're not just going to talk about how a linked list works. Like we did just talk about how arrays and array lists work without cracking those open. We looked a little bit into array lists, but that was only to talk about classes. You'll crack those open in 250. You are expected to know that as well. Linked list, we're cracking these things open right here in 116 because it's nice to know how they work. You won't have to build your own linked lists anytime in your future, except unless you go to a very, very specific career path where for some reason that's called for. But the concept you're going to apply, usually, I'd say most of you will end up applying the concept somewhere else. You'll have this idea applied outside of the linked list data structure itself. So it's good to know for that. And if you don't care about any of that, linked lists, for some reason in interviews, the interviewers love to talk about linked lists. They love to ask questions about linked lists. What's the structure of a linked list? That one you're guaranteed to get in the linked list interview when we finally get there. That's not for a while, though. But that's also a good interview question that job interviews, they like to ask. I don't know why. I don't know why. I think it's just because this is such a fundamental CS concept that they know you have seen it in class, and they're testing your ability to remember what you learned about. But they like asking about this. One question I see a lot, I don't know why, but how do you, in one pass through a linked list, find the center of a linked list? How do you find the middle element of a linked list? I'd be doing a huge disservice. I would talk about linked lists anyway, even if without that, but I'd be doing a huge disservice if I never talked about them. Plus all my colleagues would get mad at me. Do we have to count up by 4? We're counting up by 4 in that previous example specifically because these were ints, and ints in Java are 32-bit. So if this were an array list of doubles, which are 64-bit in Java, then we would count up by 8s. It's the size of the value in general. So back here, the size, whatever the size of one element is, and yeah, elements in an array have to be fixed size because of this fact, or else we wouldn't have random access. So they do have to be fixed size. That's why they're either primitives, like ints, doubles, booleans. All those are fixed size in Java. Every primitive is. And then everything else is a reference, and your references are fixed size, as we were talking about. So we are going to build our linked list from scratch, not just to torture you, not to torture you at all, but because there's a lot of educational value and it's an important fundamental computer science topic that we all just have to know. We're all just expected to know it, so we're gonna. So let's talk about what they are. The concept, that all said, the concept is fundamental, like absolutely critically important. But the reason why we're going to create our own from scratch instead of just import linked lists is to really get a strong handle on how these things work. All right. So linked lists are sequential, just like an array list. Similarities stop there. So they are sequential, meaning that order matters. The order in which we insert elements into a linked list will be preserved. Linked list does care about order, as opposed to our maps, or any key value store doesn't care about order. You throw a whole bunch of key value stores in a map, and it just stores them all. You loop over that map. You can get them in any order that Java decides. Asterisk, but I don't feel like talking about it. We don't have time to talk about it. The similarities on there, and the first thing, spread across memory. These linked lists, the values are all over memory. Where with an array, they're all in one sequential block in memory, where we can actually do memory address math to find where our elements are. That will not be true at all with linked lists. That whole thing goes away. The whole random access and accessing by index, it all goes away. Because our values are spread across memory. So the way a linked list works, and I'll explain this in like 4 different ways. So if you don't like the pure text explanation, don't worry, I got visuals and stuff. But the way a linked list works is each element, which we're going to refer to as nodes in a linked list, each node in a linked list knows 2 things: the value at that location of the linked list and the memory address by reference of where you can find the next node in the linked list. So with those 2 pieces of information, we can combine nodes as much as we want. Since they have references to each other node, the linked list can bounce all around memory, following reference after reference to find the next node and the next node and the next node until we reach, I don't have it on this slide yet, until we reach null, the end of the list. I'll talk about that on another slide. The advantage of this Memory data structures are always about trade-offs. The advantage to this is that we get variable size. One of the advantages, I should say. We get variable size. If we want to add a new node to a linked list, a new value to a linked list, we create a new node, we put the value in that node, and then we update a reference somewhere to refer to that node to add it to the linked list. We don't have to destroy the structure of the linked list we have. We don't have to move anything around memory. We don't have to create a new linked list and copy all our values over like we do with an array if we want to change its size. Since everything's by reference, we just update the references to add that element. We can even add a new element to the center of a linked list. It's no big deal. We just update the references to integrate that new node into the linked list. So we're going to use objects. This is where we need objects and references. I just used the word reference a whole bunch of times. It's not a coincidence that we just learned about references last week. Now we're going to use them this week. We needed references and objects and classes. We needed all that before we could start talking about linked lists. So each linked list node is going to be a separate object on the heap. It's going to know its value and a reference to the next linked list node object in the heap until we get to the end of the list, which is where we have a node where the next node, a reference to the next node, is null. And this is the first time we're seeing this keyword null. Null is a keyword that pretty much stands for nothing, but more accurately than that, null is when you have a variable that should store a reference, and it doesn't. That's what null is. So if I have a variable that should store a reference, so each one of these linked list nodes should store a reference to another linked list node, and if instead of storing a reference, it doesn't, we're going to store null in that variable. It's the lack of a reference is null. So like primitives, you can't say int equals null, int x equals null. You can't do that because it's not the lack of a reference. You can't have the lack of a value in a primitive. It's a lack of a reference in a variable that should store a reference. At least in Java. I mean, other languages use null just to generically mean nothing. But Java, it's the lack of a reference where there should be one. And then our linked lists, we don't actually store linked lists in variables. We store a reference to the first node in the linked list. Yeah.
How is null represented in memory?
I don't remember exactly, but I think it's like OX0. It's like a special reserved index. I don't want to commit to that one. But it's something like that. There's some special reserved memory address that's not used for any actual memory addresses, which represents null. If I were to guess, it would be the memory address 0, and that would be a reserved one. But it might be different. Hell, it might be different for each operating system or each piece of hardware. I don't know. But there's some special memory address that says this is null. That'd be a good question for Ethan Blind. He would definitely have the answer for you. What's the advantage of using linked lists over array lists? It was 2 minutes. So that was asked before I said that, but I'll go a little bit more in depth into this. It's the structure is very flexible. Since a linked list really takes advantage of the heap being this kind of nebulous, flexible space, and it's creating new objects on the heap and then using references to link those objects together. It makes your linked list very, very flexible. If you want to remove elements, add elements, remove elements from the middle, add elements to the middle, you can do all of those things very, very efficiently. You cannot do that with an array. Say you want to remove the center element from an array, or even if you want to remove the first element of the array, that's actually the worst case scenario. If you have this array of 1 million elements and you want to remove, I always do this backwards. This one would be the first one, right? From left to right. Yeah, because it's always, I got to do it backwards. If I have an array of 1 million elements and I want to delete the first one, and I want to just flat out remove it from the array list or the array, I remove it and then take 999,999 elements and shift them all down by 1, which is going to take a lot of time and a lot of memory manipulation. Same thing if I want to add an element into index 0 and push everything down by 1 index, I got to copy all of that information down by one value. With a linked list, both of those things are trivial. You just create a new node and have its next refer to the old first node in the linked list, and then you're done. It's super easy. Bless you. The trade-off is that it takes a long time to navigate to a specific element. So if you have your linked list of 1 million elements and you want to get that 800, bless you, and you want to get that 800,000th element, like we did it with the array list, we just did a multiplication and an addition with an array or an array list or any random access data structure. You just do a multiplication and index, that gives you the memory address, and you go right over to that memory address, done. With a linked list, guess what you got to do? You go to the first node, you say, hey, where can I find the next node? You ask that node, where can I find the next node? And you bounce all over memory 800,000 times before you get to your value that you're looking for. So those are the trade-offs between these two. We lose random access, but we gain flexibility. So it depends on your application, whatever you're doing. If you have data that's constantly changing all over the data structure, linked list might be more efficient for you. But if you need to access elements in the middle of your data structure very often without manipulating them, then random access with array list is going to do it for you. All right, so here's our linked list node class. We're going to start with this linked list node int class. We will, on Wednesday, change this to linked list node, and then we're actually going to take a generic parameter or a type parameter, just like an array list does. We can create an array list of any type. This one, just to start, just to keep things a little simpler for the first example, I'm going to hard code it to be a linked list of ints. But we will change that later on Wednesday. So this linked list, yeah. It's not inheritance quite yet, but we will get there. So yeah, we will get to inheritance. That's coming up soon, ain't it? Is that next week? Oh, wow. Yeah, that's coming up soon, next week. So I feel bad that I had to ask that I don't know off the hand. But I did move 1 week, the testing week. Next week used to be the testing 2, and I moved it to just to accommodate the schedule. So this, what I have highlighted, these 6 lines, that really is the linked list node. This is all we need for the linked list, is these 2 instance variables. So 1, the value stored at this location in the linked list, and 2, a reference to the next linked list node in the list, so we can find the rest of the list, the next values. And then a constructor, I just have a constructor to be able to set those 2 values of those 2 instance variables. And really, strictly speaking, that's all we need. That's all we need for a linked list. Now, we'll write more methods to actually do something with the linked lists. We don't even have getters and setters here, so this is only useful if we have our code inside this class itself. So we'll start expanding this. We'll expand it throughout the week. But really, all we need is these 2 variables, these 2 instance variables, and the second one is a reference to an object of its own type. Visually, it's going to look like this. Oh, I want to walk through this code, actually. So if we run this code, if we do this one line at a time, and we will break this down in a memory diagram too. I'm going to show this in multiple ways. We're going to see this a bunch of times to get the structure of a linked list down. But first, let's just walk through the code. So we're going to create a variable named first of type linked list node int that's going to store a reference to a linked list node, which is going to store our list itself, which we would think of this as storing our entire list, but it's actually just a reference to the first node in the list. And through that first node in the list, we can find the rest of the list by going .next, 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 until next is null. We can navigate through the entire list. So first we initialize this to a new linked list node with the value 1 and next of null. So this is going to be effectively a linked list of size 1 that stores the value 1. Its next is null, so it's already the end of the list. And there's nothing else in the list. Then this line gets a little bit tricky. So let's break this down a little bit further. We're going to create a new linked list node. Whenever we have an assignment operator, it's important to know we have to evaluate the right-hand side first. We resolve this down to a value, and then assign that value to first. because we have the variable first twice in this single line. So what's the value going to be of first going to be? Well, it's going to depend on where we are in the evaluation, because its value is changing after this line executes. So when we execute this constructor, we resolve the parameters before we can call the constructor, before we can get to that stack frame. And at that point in time, first is still a reference to this linked list node here. So we give it a reference to that first node, the old first node, the first node that we created, create this new linked list node with value 2, and its next being a reference to this linked list node, and then reassign first to a reference to that second node that was created. And then we do that again, create a new linked list node. At this point in time, first is a reference to this linked list node, whatever this constructor returned, and then reassign first to a reference to this node. So after all of this executes, first is a reference to a linked list node with value 3, with a next, which is a reference of a linked list node with value 2, with a next that's a linked list node of value 1, with a next of null, meaning it's the end of the list. So what we effectively did here is prepend values to a linked list. We created a new linked list with value 1, prepended 2, and prepended 3, meaning we're adding elements to the beginning, to the front of the linked list. Yeah, linked list is the guy and they tell you not to worry about. So in the JVM, when I was answering the question about references, the null reference, the JVM abstracts everything away. I was thinking more at the OS level. The JVM just abstracts everything away. Can you explain the working of the second instance variable? Workings of the second instance variable. So this is a reference to the next node in the list. So at the end of this code, first is a reference to a linked list node where value is 3. That's the value at that list. Like that's the important bit. That's the part we're actually interested in with this linked list. The first value of the linked list is 3. Just like with an array list, this would be the equivalent of having 3 stored at index 0. But there's no indices in linked lists. We have to follow these next references. So the next reference is a reference to the next node in the linked list, which is where we can find the second value in the linked list. And then the third value, then the fourth. So this node has a value 3 and a next referring to this node, which has the value 2, and the next referring to this node. So next is where we can find the next node in the list, or effectively the rest of the list. Yep. Yeah, because we're prepending to the front, we started with 1, prepended 2 before it, and then prepended 3 before that. So it's 3, 2, 1. There sure is. I'll explain how to do that, and I'll do things very similar to that. It's on your programming test 3 where you'll have to do that. So I'm not going to explicitly give the code for append and code. Append to the end and prepend to the front. Yep. The way that I specifically built this linked list, I was doing it in reverse, yeah. That's not always the case. That's just how I built this one. It's the simplest way to add things to a linked list. So for a first example, I wanted to prepend. Just because I can do the whole list, I can build the whole thing in 3 lines. Yep.
So in the last lecture, you said that if we remove any way to access a reference variable, it will Java automatically remove it from the memory. Like if I remove any way to access the first variable, which is storing the value 3, will the next and the next value be removed as well from the memory?
Yes. Yeah. When we get to the memory diagram, when I have the visual, I can explain this a little better. But the question is, won't these... Well, you asked a more advanced question than this, but let me build up that in 2 steps. So the first question would be, this looks exactly like the first 2 lines in our last memory diagram on Friday, where the first node got garbage collected. We had the 2 characters and that hero character. It was garbage collected because we reassigned it. It looks identical to that. But I was very careful in the way that I worded that, where I said, as long as we have access to a reference, it won't get garbage collected. Once we no longer have access to a reference, that's when something gets garbage collected. But we do actually still have access to the reference to this first node, even though it's not on the stack anymore after the second line executes. It's not on the stack anymore, but we can still go through first.next to still access that object. We do still have access to a reference to that object, so it does not get garbage collected. Then to answer your question, if, say, I added a fourth line that said first equals new linked list node of 4, null, then I would no longer have access to the first 3 nodes, and they would get garbage collected. But as long as they're accessible somewhere, somehow, through any number of jumps across the heap, as long as I can somehow get to that object still, it will not get garbage collected. So visually, it looks like this. My variable that's on the stack, the only variable that's on the stack, only stores a reference to the first node of the linked list. So first is a reference to the node that has the value 3, which has a next, which is a reference to the node with the value 2, which has a next, which is a reference to the node that's with the value 1, which has a next of null, indicating that it is the end of the list. So this is what that linked list is going to look like from our slides. So, and we think of this as a linked list, but really it's 3 node objects in memory, and we're taking advantage of these references, storing references, having objects storing references to other objects. There we go. And using that to create a linked list out of linked list nodes. Can linked list nodes access the previous node? No, they never can. Our linked list nodes in 116 will not. There is something called a doubly linked list, where each node has a next reference and also has a previous reference, so it knows the previous node in the linked list. We're not going to do that in 116. I believe they do that in 250. I'm almost certain they do. They'll do doubly linked lists there, and you can talk about the differences at length. We're only going to do singly linked lists in 116, it came up in the other lecture, so I'll go a little further on this. Doubly linked lists do have more functionality than singly linked lists. Not really functionality, but there are more things you can do for optimizations with them, especially if you store nodes to the front and back of the linked list, and you want to manipulate the back of the linked list. There's just different things you can do with that. In terms of efficiency, you don't get any more power, but you get more efficiency for certain applications. But that doesn't mean singly linked lists are never used. These are used in the real world quite a bit. So it's not like you learn doubly linked lists and throw away singly linked lists. Primarily if you want immutable data structures. So you want data structures where they cannot be changed, but you still want to be able to modify them, which sounds counterintuitive. It sounds like you can't do that. But with a singly linked list, you can actually accomplish that. If this list doesn't change at all and can't change at all, but I still want to prepend an element, I would have another node that I create and have it refer to this node. This list didn't change at all. I just have another node referring to it. If it's a doubly linked list, I got to update previous here. This linked list has to change, and I can't have an immutable data structure. But that's a conversation that's beyond what we want to do in 116. Suffice to say, singly linked lists don't disappear just because you learn doubly linked lists later. What happened to the lecture recording online? All the technology was broken on Friday, unfortunately. We lost the recording for Friday, unfortunately. So you can only access the values for the first time by working backwards, like recursion, basically. Mm-hmm. What type of data are linked lists useful for storing? Anything? I don't know. Anything you want to store? Anything you want to store in your linked list. We are going to use recursion. And looking at the time, I better get to that recursion. Can the last node point to the first? Yes, but it shouldn't. So instead of referring to null, if next refers to the first node, you shouldn't do that. Technically, it's possible. but you're going to go infinite in most of your algorithms, including the very first algorithm, toString, that we're going to see today. So let's see this in a memory diagram. Because I think it's more clear when we see it in the memory diagram. And this starts off just the same as any memory diagram. Goodness gracious, you better be great with this first line. This has nothing to do with linked lists. This is just a constructor call creating an object on the heap. If you're not feeling good about this first line, you need to study because this is most of the quiz this week. You got to be good at this. But we're calling the constructor, creating copies of the instance variables. This constructor assigns the parameters to the instance variables. This is a reference to the object being created. This returns a reference to that object that was created when the constructor stack frame ends. And we have our linked list node with value 1. 350 I made up. It can be any value you want, but you need to be consistent. Wherever 350 should appear, you need 350. Okay, the second line does get more interesting, though. This is where we have to think about linked lists, and we have the variable first twice on one line, which trips students up, reasonably so. So let's break this down. We have to evaluate the right-hand side first. So we're going to have a constructor method call. We need to evaluate the arguments before we can put that method call on the stack. You can remember this if you don't remember that any other way. Whatever's in the parentheses is evaluated first. Just remember your math stuff. You'll get away with that. So inside the parentheses, we need to evaluate first before we put this frame on the stack. First, we're in the main method when we have to evaluate that. So we look at the value for first, and it's 350. So that way we're not getting tripped up on getting the wrong reference in this constructor call. So first is OX350. That means next is OX350. Creating a new linked list node. And these linked list nodes can be all over memory. Each node can be anywhere in memory. I chose 200 just to show that this can be wherever. I'm just making up numbers for those. So this is a reference to the object that's being created. So this linked list node gets next of 350. That returns to first. So now first is updated to the reference of the object that was just created. First no longer stores the value 350, it stores 200. 350 is no longer on the stack, but first dot next, we can still access OX350. We have a reference to that object, so it does not get garbage collected. It doesn't matter if that reference is on the stack or not. As long as we have some way of starting at the stack and accessing that reference to that object, it does not get garbage collected. In most cases, none. What's the advantage of linked lists over array lists? All right, so then we do it again. At this point, first, when we were evaluating this, first was OX200. So OX200 is next. I made up 480 for this reference. And then first got the value 480 when that constructor returned. So first is just a reference to the first node in the linked list, not a reference to the entire linked list. First is a reference to 480, which has a value of 3, which next is 200, value of 2, next is 350, value 1, next is null, meaning it's the end of the list. So we created our linked list with 3, 2, 1 as the values, and that's how we did it. That's how it looks in memory. I did it again. I knew I was going to do it when I reviewed the slides. I did it in the last section. I did in this. I said all 3 slides of content in the first slide. Yep.
When you use the heap or the node or the next variable, like as a reference, what happens to the null? Like, does the this dot next make the most recent one null?
So this one's null because that's what we gave the constructor. But for the other 2, we gave an actual reference to the constructor instead of null. We can replace this null if we did like first dot next dot next dot next. I think I said one too many there. I don't know. Equals new linked list node. We could actually add to the end of this linked list. We would cross out this null, write in a reference, and create a new node, if that's what you're asking. Yeah, null is the way that we say this is the last node in the list. That's what we're using null to indicate. The null is the lack of a reference, so we're saying there's no more nodes to look at. You're done looking at nodes. That's what null is going to mean for us. Which will be important in 220. Even your strings are going to be null terminated. So getting used to seeing null indicating the end of a data structure is going to be important. All right, let's see a toString. And guess what we're going to use for toString? Recursion. Yay. So we're going to see a lot more recursion this week. And I'll be honest, you don't really need recursion. Some of you will write loops on your homework, and I'm not going to stop you. But I do encourage you to use recursion whenever you're working with linked lists, because you're really going to want to use recursion when we get to trees. Trees is going to be our big recursion payoff. And if you're writing your first recursive methods on trees instead of linked lists, it's going to be difficult. You're going to have a lot of trouble writing those recursive methods. So let's jump right back to a memory diagram and look at how this toString works. So I'm going to explicitly call toString. We can do print line of first. That will have the same effect here because print line will call toString. I'm going to break it into two lines just to be explicit. So we call toString first dot toString. So this is going to be OX480. We're going to get 3 in our output string, and then if this dot next not equal null, it doesn't. It is storing a reference, and we're going to have lots of these null checks when we're dealing with linked lists. If next is null, this is the last node, treat it differently than our other nodes. Next is not null here, so we get our recursive call. This dot next dot toString, we're calling toString from this node, so this is OX200 with the value 2. This dot next is not null. We're going to make another recursive call with 350, and then this dot next is null, so we skip over the condition and start returning. We're going to return 1. Back to this stack frame. This stack frame gets control again. It just got the return value of this recursive call, which was 1. It's going to append or concatenate 2 and space 1. Return 2 space 1. Gets its return value 3. Append space 2 1. Then return 3 2 1. We get the entire value of the linked list concatenated and returned as a string from this recursive call. Yeah. Concatenate when we combine two strings, the plus operator on strings. That's what I'm referring to as concatenate. Is that your question?
Oh, yeah.
Cool. And then we get the whole thing printed to the screen. And notice we only called this on the head of the linked list on OX480, but the recursion kept going this dot next, this dot next, this dot next, until this dot next was null, and was able to get all of the values concatenated together. Then the program ends. My music driving me nuts. Why?